So are we back? Is it 12:55? Yes. So is Krishnendu here?
Yes, I'm here.
Okay, so for our next talk, Krishnendu Mandal is going to speak on modeling acoustic wave propagation in solar interior for helioseismic measurements. And I'll give you a warning at 8 minutes, which means you have 2 minutes left before a 5-minute discussion. Thank you.
No. Do you see my screen?
Yes, we see it and we can hear you.
Yeah. So today I am going to talk about modeling acoustic wave propagation in solar interior for helioseismic measurements. So why solving the wave equation for the sun in the finite frequency domain is computationally very expensive. So that's why like earlier people use array approximations instead of finite frequency approximation for to measure the effect of different perturbations in helioseismology. But the approximations, that is like infinite frequency limit up, and so that is the limit where we assume that the frequency of the waves is infinite. But there are many effects for which like we need to see like how finite frequency is affecting finite frequency of the waves affects the perturbations. So to test this, like we need to have some code that will take into account like the finite frequency effect. So we solve this problem in spherical harmonic domain and temporal frequency domains. And use parallel computations to accelerate the computations. So our governing equations is equation of motions. So this is equation of motion. So this is wave displacement. This is displacement vector. Xi is displacement vector. Omega is frequency, and subscript 0 corresponds to the background values, and prime corresponds to the perturbations. So we have equation of motions, equation of continuity, and we assume that waves is adiabatic in nature, and n square is the Barnes-Forsler frequency. R is the radial displacement, and H corresponds to the horizontal values. And our background model is model S, and for the source function in this equation, we use delta function source, radially directed delta function source. So in these approximations, like we can so if we decompose this equation in the radial and the horizontal domain, so we'll get this the horizontal displacement will be related to the pressure perturbations. So then we can express this. So the whole equations will be converted to, there will be only two independent variables. Those are xi r and p prime, and we expand that in terms of the spherical harmonic basis. So alpha lm and beta lm, they are in the spherical, they are the unknown coefficients that you need to solve for. So in the matrix, so if we write it in the matrix form, this will be the equations, and we assume that the boundary condition, that the radial displacement, so this is, we solve our boundary domain is from 0.2 solar radii to the 1 solar radii, and near the bottom boundary we consider the radial displacement is 0, and near the top boundary we consider that the pressure perturbations is 0, and we use finite difference method to discretize in radius and solve these equations. So then we test like after solving the equation, we test it for like the test is something that we have the another way to measure the values, so such as array approximations. So this is the time distance diagram. So this is that, so this distance corresponds to the separation distance between two observation points, and this as you can see, like these are the waves which if it appears like after the first bounce, this is after the second bounce. So this corresponds to different bounce, and the red solid line, that corresponds to the like the values that we obtain from the ray theory. That both the wave approximations and ray theory, they corresponds to the like this they correspond reasonably well. And this value, this is one of the wave packet that is arriving around 40 degree separation distance between two observation points. So then we compare it with the like power spectrum. So this black marker, that is from our simulations, and this red markers, that we got it from the MDI measurement. And you see that the frequency and our observations and the simulations, they agree quite well. And this is one of the like cut through, like for harmonic degree L equal to 100. That this black dash line, that is from MDI observations, and solid line, that is from the simulations. So the frequency that we are getting, they're quite well with the observations. So now we want to test it for the like for some background, if background medium is part of like, so in our case we consider model as that is spherically symmetric background model. So but if there is any axisymmetric perturbation like sound speed perturbations in the interior of the sun, like there are two observation points, this is on the surface S and R, and waves are propagating, and if there is any perturbations in the medium, axisymmetric perturbations, how that will change the travel time. So we relate it using the, so if it is weak, we can use the linear perturbation theory and calculate. So this can be related by using this linear integral equations, where delta C is the perturbations and Kc is the Kc we call the sensitivity functions. So Kc can be calculated using the like the zeroth order model, and so this is how it looks. So this is on sensitivity kernel for the sound speed perturbations. And these two are the observation points, and this black dash line, that is the ray part, and these two are the observation points here. So if you say like according to the ray theory, you should see like there should be, so all the power is concentrated near this part, but using the finite frequency domain, like we see the sensitivity around this part is almost zero. So this is in the R5 domain, like radius and longitude. This is how it looks in the latitude and longitude domain, and this is in R and theta. So this is called banana donut kernel. So now you want to test like how accurate we are measuring this sensitivity kernel. So we need to do some validation test. So for validation test, we consider like one perturbation, so that is spherically symmetric. So the perturbations in the sound speed, that we consider spherically symmetric. So if it is spherically symmetric, then this can be used as a background model, another background model for our simulations. So this is the starting model CR, and another background model, that is CR plus delta CR. We will do the simulations and get the waves from these two models, and then we measure the change in travel time. And this travel time, then again in the second step, we consider this as a perturbations and calculate calculate using this kernel, sensitivity kernel. So these two can be compared. So if they match very well, then we can say like they are we are validating these approximations. So this is one of the tests. Like this is the left panel is for sound speed kernel validation test for the sound speed kernel, and the right panel is for validation test for the flow kernel. And so these are for different separation distances. And so in the bottom panel, I am considering the difference between the exact value and the analytical value, and the value that we are getting from the linear perturbation theory. So they match quite very accurately, like 0.026%. So it is very accurate. Even flow kernel is around 0.02%.
In 2 minutes before.
Yeah, thank you. So we can quite accurately calculate this sensitivity kernel. And so coming to the conclusion, so the effect of perturbations can be measured with high accuracy in the time distance helioseismic framework. So this study can serve as a test bed for helioseismic measurement, including time distance ring diagram and normal mode traveling analysis. So here in this work, I have only shown like how it can be tested for time distance, but the other helioseismology method can also be tested. So So if you have any ideas, those are welcome. Thank you.
Okay, thank you very much. You're getting lots of applause here. And I see some applause, but no questions yet. Does anybody have any questions for Krishnendu? Our helioseismologists in the audience, perhaps.
Junwei.
Oh, Junwei?
Yes. So I'm wondering if you are able to insert magnetic field in this work, because these days the detection of interior magnetic field has become one major concern for future studies. So
yeah, that can be tested like by calculating how you can take into account the Lorentz force as a perturbations. But I'm not sure like if the like this is what we do in the linear perturbation theory. But if the like there is nonlinear effect due to the magnetic field, like mode conversion, so it can be a bit tricky. But if it can be treated using linear perturbation theory, I think that is possible.
Thank you. Good question. Anybody else? Well, if you think of another question, please drop it in the chat. If not, we'll go on to our next speaker, which is Irina Kitiashvili. It looks like we're having the New Jersey Institute represented well in this later half of the day. Irina is going to be speaking on realistic 3D modeling of the sun connecting interior dynamics to the atmosphere. I'm not seeing your slides yet. Irina, are you sharing your slides? I'm seeing Depayan Banik. What's happening here?
That's what I'm also seeing.
Yeah, I think that's just Irina's Zoom.
Irina, are you attempting to share your slide deck with us right now?
We can't hear Irina either.
Okay. Sasha, are you here? Do we want to, let's see, alphabetical reasons, I guess.
I mean, that's Depayan is pinned in Irina's Zoom there, I think.
Okay, but I am not hearing anything from Irina, which makes me think she is not online right now.
Okay, can you hear me now?
Oh, yes. Okay. Great. I was worried you weren't here. Yes, we can hear you, but we can't see a slide deck yet.
Yeah, start discussing. Okay, can you see my screen?
We see a screen with the name Depayan Banik on it.
Now you should see my slide.
No, we do not see them yet.
Okay, I will do this one more time. Probably I should choose different option, share screen.
I think you're probably choosing your browser to share.
Of course, I'm not allowed to use Zoom.
Maybe if
There
you
we go. We can see a slide now.
Okay, which mode?
It's
Good.
It's fine for me. I can zoom in and out on it. I hope it's good for everyone else.
All good.
Okay. So you take it away and I'll give you a notice when you're 8 minutes in, that you have 2 minutes left before discussion.
I believe I have 15 minutes. No?
You have 15. We said 10 minutes for presentation,
Okay,
5.
okay,
If you want to eat
whatever.
into your discussion time, that's fine.
Okay,
but we'll end at
whatever.
15.
Let's continue. Okay. So, so it was originally 15 minutes presentation. So I want to apologize what I have skipped many things there. So I will try run as fast as I can. So I'm going to discuss some results from 3D realistic simulations of solar convection. And the general idea behind of these simulations is to provide a robust data set to community, and also investigated by myself to understand how dynamics of subsurface flows actually affect on surface observations. And in particular, this slide is just illustration of, for instance, like HMI observations, and you can do tracking of region, and using heliosmology approach, you can reconstruct subsurface flows, and also, of course, which can be affected by different phenomena like rotation of the sun, and also emerging magnetic flux, some reorganization of magnetic flux, and so on. Okay, so and of course, for future, of course, it is kind critical to do like study through different stages of solar activity. And for this study, just when we discuss about coupling of subsurface and surface dynamics, of course, we first think about global models, which usually truncated by just most important layers to actually do observations. But nevertheless, of course, it also was discussed today many times. It is a lot advantages to do global simulations. And also, we discussed earlier today on new approaches to actually solve such problem like absence of actual photosphere. And local models actually develop really well, and many studies try to use a local modeling approach to study different regions in convection zone, for example, Berinkart models, but also many realistic type models can actually see coupling atmospheric layers and subsurface dynamics. And of course, maybe most important ingredient of this is connection to observations, because it first, of course, allow us to validate our models and also provide important physical insight to observed phenomena. And how to do this? It can be done in different way. Most direct one is generate synthetic observables and use them to perform more kind of robust comparison between models and observations. And of course, we always can do a comparison. Maybe in some cases it is more tricky in terms of interpretation, but more direct comparison between models and simulations when we try to look distribution of certain parameters, say like first most basic, for instance, example of such comparison, just compare scales what we have in simulations and observations. And in this work, I'm going to discuss about stellar box simulations. And first, I want to illustrate our simulations, which actually suggest a shift of paradigm in understanding structure of subsurface convection. And on left, you see a well-known paper by Aki Norland and Bob Stein and Ashbrund, where in hydrodynamic simulations, we can see actually increased scale with depth. And more recent simulations on right for larger domain, and actually it is a deeper domain, we see kind of similar structuring. So we see increased scales, but if you go even 5 megameters below, you still can potentially can say maybe it is increased scale, but it is not as obvious as you see on left image. If you go even deeper, in this case, again, 7 megameters, it kind of like maybe yes, we have increased scales, maybe not. But when we go deeper and deeper, we basically cannot really discuss anymore about increase of scales. And from one side, it is, I just keep on left image from previous studies. From one side, we see a clear discrepancy with recent simulations. But actually, if you look in more detail, yes, and first I want to discuss origin of this. Actually, reason why we lose such property as increase scales in terms of visual inspection. We see what actually we when we discuss about near surface layers, we see kind of very strong imbalance between upflows and downflows. But as we go to deeper layers, distribution of upflows and downflows getting more and more symmetrical, and it is main reason why we really don't see such discrepancies, such large-scale structuring. But if you look at turbulence spectra, we still see increase of scales. So what it basically say, it is some paradigm shift, but I want just to warn, like especially people who do global modeling, if you see just a visually increase in scales at deeper layers, maybe it's relate not just because of just general increase of scales, but also probably it is because we are not resolving well enough turbulent flows, or convective flows are too strong. And next topic what I want to discuss is actually effect of rotations on rotation on turbulent structure of subsurface layers. And on this slide, on upper image and lower image on bottom, you see actually self-developed differential rotation. And the difference between these two images, basically in on upper plot, you see our period of rotation like 27 days, but on bottom, it is more realistic rotation rate imposed in our computational domain. In both cases, we actually run really for a long time to get, it is, I cannot say steady state because as I asked previous speaker, it is kind of sometimes tricky to estimate, but we run actually many hundreds of hours to get this state. And what you see basically structure in terms of distribution of azimuthal flows vary quite a lot. And the difference between rotation rate really small. So it basically means what we really should be very, very careful when we impose a certain rotation and try to interpret results, because as you see, results can vary quite a lot. But also, even in a case when we don't have magnetic field, such we observe evolution of both azimuthal flows and meridional flows. And basically, it means our results sometimes can depend from period of time which we select for analysis.
Irina, you're 9 minutes into your time, 9 minutes in.
Okay, I'm going to skip it. Just for this case, we see special layer. It is, we call this leptocline. And this leptocline reflect actually transition between two different layers, like more and less convectively unstable layer. And this result was actually confirmed many times in observations. And just in response to previous speakers, actually local simulations able to reproduce meridional flows. And we do a lot analysis on helioseismology. And because of time, I probably have to skip it. And we do study actually center to limb variations and see how different modes are affected by solar rotation. And unfortunately, I have to skip it and just go to more main point for this. We see actually in continuum intensity east-west asymmetry, which manifested as suppression and enhancement different modes when you look when you direct it to disk center or to limb. And it is my conclusion, and I will stop there. Thank you.
Oh, thank you so much. That looked like a lot of rich material. I see a lot of applause. What questions do we have?
Can you put your conclusions back up, please, Irina?
Yes, please.
Sorry. I tried to find how I can do. I didn't realize I'm allowed to share screen. It is share entire screen. I don't know which screen I'm sharing.
That's it. You got it.
Okay, good.
Okay, Sasha has a question.
Thank you. I'm wondering if we know that convective cells rotate faster than the surface. And I'm wondering if you see this effect of, because convection becomes a kind of a running wave when you have rotation. It observed very well in supergranulation, but I'm wondering if you see something similar in granulation, just patterns of convection.
Actually, yeah. Thank you. It is actually a very interesting point. Honestly, I never look at this. I should do tracking of granulation, and I'm not sure if granulation is a good pattern for this, because on very short scales, it is unlikely I will see this on granulation level. But
well,
maybe
if you have a gradient of rotation, then it's what theory predicts, simple convective stability theory, that these are running convective waves.
Yes, I understand this, but problem is time scale, lifetime of granules are probably too short. You see,
okay.
and but we see large scale convective patterns like similar to supergranulation, and it will be interesting to try check this. But it's hard to say what I will get.
Thank you. You just briefly showed a slide regarding the intensity differences between East and West. I didn't understand that at all. Can you say something about that?
You mean this?
No, the other ones that showed rays that were blue and the East-West asymmetry. What is this?
It is basically we try to look ring diagrams.
Mm-hmm.
And you see actually when we go closer to limb, we see suppression of modes in like in this half, which directed in direction to disk center. But what is interesting about this, in continuum intensity, we see really good signal to noise ratio towards to limb.
So it doesn't have to do with rotation; it has to do with where it is on the disk.
It is okay. In this particular case, it has nothing to do with rotation. You are right. As you see on left, we have same kind pattern, just reversed. But if we do comparison, I included only like a case for Doppler shift, and I do comparison of I just made slice different frequencies. And we see first, due to rotation, variations in amplitude of different modes. But also we see in high frequencies, we see actually slight shift of modes. And I think it is due to rotation, because I should mention data set absolutely identical. Doesn't matter. It is I look in data on East or West, just they're absolutely identical.
Okay, thank you. Well, if there's no other questions, let's thank Irina again. And I think I spoke earlier and mentioned New Jersey Institute. Of course, you're at NASA Ames.
No,
You're
no, no,
sandwiched
no
in
problem.
between two. What?
No
You're
problem.
sandwiched
Long
between
day.
two people in New Jersey.
No problem.
I misspoke.
Don't
Sorry
worry
about
about
that.
it.
So
No
our
problem.
next speaker is from New Jersey Institute of Technology. It's Alexander Sasha Kosovichev, who will be speaking on the structure, dynamics, and magnetic helicity of emerging active regions. Go ahead.
Irina, can you stop sharing?
Yeah, we have to stop sharing and then change slide deck. Thank you. We don't see your slides yet, but it says you're screen sharing. There we go. We can see them and we can hear you. Thank you.
Okay, so what, my brief talk will be mostly about how we connect local observations of active regions to global dynamo models. So first, we look at what we use helioseismology, local helioseismology to map flows and beneath the active region, particularly emerging active regions. So this helioseismology that we developed for HMI, it used two different techniques for emergent travel times and two different inversion techniques. So what we have kind of, 4 different data sets for this. So it's to check robustness of these measurements. So what Irina already showed, similar movie of emerging active regions. So actually what we develop a pipeline specifically for tracking emerging active regions. So to identify active region emerging within plus minus 30 degrees from center of meridian and track before emergence and after disappearance in 11 layers beneath the surface of the sun from 0 to 30 megameters. So it tracks for 10 days the whole history of active regions. So I'll show some of them. So it's one of these active regions. Some people are excited about anti-active regions, but what I look, what it's actually very interesting. It was very brief. It formed also by kind of sharing flows active region, and it produced a big flare, X1.5 flare. So sometimes these anti-hail emerging active regions are important, but generally they live very brief and probably fluctuations of a general part of emergence. I show some movies of two large, it's the same, sorry. So two large active regions that I also discussed today a little bit. So these active regions produce a lot of activity. And so this is a movie of active region 13664. And we can see how it's the depth of 4 megameters. And we can see how the surface flows actually drive that magnetic field. And sometimes we can see actually that when we do surface tracking, then you don't see flows across magnetic field. And here and magnetic field, of course, on the surface here. And so it's some interesting flow patterns that we need to understand, and they definitely affect evolution of active region. This is another active region that also produce big flares, and we can see polarity inversion lines that forming also by sharing flows. So this is quite interesting phenomenon, and very often before emergence we can see vortex flows in there. So it's kind of a study that we are trying to make systematic study of this. And also in local helioseismology, we actually construct three-dimensional flow field. And the patterns look very interesting. So it's the same active regions at some moment of time. And now we can see from kind of beneath the surface, you can see from inside the sun to the top. So it shows the colors, shows the distribution of the sun-speed variations. And here I plotted some streamlines from three-dimensional flows that we have from that time distance helioseismology. And here we can see that near the surface, we can see just beneath the sunspots, we can see areas of suppressed sound speed. And surrounding, we can see a lot of enhancement that was discussed, some thermal shadows are discussed, and also the drive the surface flows beneath the active regions. So this kind of interesting. Obviously, some vorticity it also discussed today. We can see it in observations. So here I show what actually interesting to look how active regions is formed by looking at sound speed variations. So here average sound speed horizontally over the whole active region, it is plotted the function of depth and time. And here we can see some glitches around April 30th. It's some glitch in the HMI data. But we can see that how its sound speed increases below the surface. And this what we call the thermal shadow. We can see kind of 3 distinct layers here. That at the top 2 megameters, where that was suppression of sound speed by sunspots. And then below, from 2 to 10 megameters, you can see enhanced sound speed. And then kind of area of orange area that what no structures. We can see some kind of vertical stripes here. So what it looks like, previously we saw in MDI data, and was when we showed this first was a lot of laughing that your sunspot is growing from above, and it's actually true. What I think, it's really sunspots growing from above at the surface, they form at the surface. And here that what I did analyzing this picture, I plotted divided in here in these 2 layers. It's a top layer and the layer below 20 megameters, and compared with first with magnetic flux. So we can see at the bottom left, we can see that it's a good correlation of sound speed with total flux. But what about these bottom layers? It turns out that it correlates with a flux rate, with flux emergence. So we do see emerging events, but they kind of not, magnetic flux is not accumulated there. It continued to rise, and actually this shows, this observation shows that evidence that sunspot active regions really formed in the top 10 megameters layer probably. But we do see this correlates. It was surprising that we see correlation with the flux rate of sound speed variations. So then we look also at these shearing flows. They relate to activity and what various characteristics and like the divergence, shearing flows, and helicity. And turns out that flow divergence it best correlates with activity, and in fact negative divergence here means convergence, but in fluid mechanics we plot divergence. So this was for both active regions. It's not exactly, cannot exactly predict probably flares, moment of flares, but periods of increased activity, they kind of correlates with flows. So then what's interesting is that if you look below, that also Rajaguru discussed today, that if you look in deeper layers, so at the top 5 megameters, we can see convergent layers that actually affect the flare activity, but below 6 megameters, all flows are divergent. So that is similar to what Rajaguru showed. So it kind of, what sharp transition in these layers in flow patterns that we see. So now how we relate this to dynamo. So previously we developed a dynamo model based on mean field approximation, and this approximation, unlike previous talks, we're not trying to resolve all turbulence, but here that was used what's called Reynolds averaging. So average over small scale and model small scale. This was similar to what people who model airplanes and Formula One cars, and they used this Reynolds averaging technique. So it's similar to this. So what we don't try to resolve from directly, because otherwise it's dominated mostly by numerical viscosity. So it actually I previously showed this several times, this model, and now what is it reproduces a lot of phenomena. Particularly, what we are happy that we are able to reproduce an extended solar cycle. But now we look at the contribution of surface bipolar magnetic regions to this dynamo model. So we included in this model. Do you still see my presentation?
Yes, we could still see it, although it just reverted to the first slide. But just a second ago, it was on the model, the Pippin and Kosovichev.
Yeah, I don't know what happened, because it's I probably need to. And now I have to. You see it now, right?
Yes, we see the video.
So what let's skip the previous slide. That we showed that initiated emerging active regions by buoyancy instability at the edge of dynamo waves, and here you can see some example of how it's dynamics inside the sun. So what's interesting that in active regions, of course, important parameter that studied in terms of dynamo is magnetic helicity. So what this plot on the top plot shows that butterfly diagram that we try to model cycles 23, 24. And by applying the initial perturbations inside the sun, so we didn't have flux tube, we didn't have any kind of just to initiate buoyancy instability, you need to apply some perturbations. The perturbations were according to distribution, longitudinal distribution of observed on the surface. So what we didn't find a better approach yet. But here it reproduces quite well evolution of magnetic flux, and also in the middle plot it reproduces helicity, hemispheric helicity, and inactive regions, and also helicity fluxes. So then we look at the balance of helicity, and I don't know how much time I have, but here that what's important that also contribution of
You're 9.5 minutes into your talk.
Okay, so what then I just switch to conclusions, if I can.
We have a few minutes before we have the questions.
Oh, this again. So it so this shows that what some evolution of emergence of active regions actually that several effects we discussed today is that what twist and share of active regions, and we can model these, in particular that what the twist share in these is modeled by that Lorentz force in this emergent flux tube, but also we included a magnetic helicity of unresolved turbulence. It's modeled as unresolved turbulence as alpha effect. And here this was an example when twist was during emergence of active regions, and we can see on the middle plot that magnetic helicity and helicity fluxes on the right plot. This is the next example that this movie shows emergence of active regions when a turbulent alpha effect, actually it was applied before the emergence, and we can see that during the emergence, this shear and flows that are generated that actually cause the tilt. And tilt relaxed, compared with observations, relaxed pretty fast, that's what we found. So then conclusions that of this, that what we find by helioseismology, that strong shear and twist and flows, they formed in subphotospheric 6 megameter deep layer during emergence evolution of active regions, and probably magnetic flux accumulated in top 8-10 megameters layer, so it's elliptic line. And below that, variations of sound speed correspond to the flux emergence rate, meaning that magnetic flux is not accumulated there, but emerges with a speed of up to kilometer per second at this layer. And then what we found, the convergence of subsurface flows increasing before periods of major flares, and also what modeling of emergent flux, in particular that what unresolved turbulence alpha effect during the emergence, it plays a significant role and in twist and tilt of active regions, and this is affected in magnetic helicity, and but these effects during emergence they kind of very transient, and finally that what my hemispheric helicity role and tilt of active regions is controlled by the differential rotation. So what I refer to this recent paper that published this week, that what we can look in more detail. Okay, thank you.
Thank you so much, and thank you for staying on time to all the speakers, actually. So I'm sure that there'll be some questions as people are raising their hand. I have a question. You stated that the sunspots are forming in a layer that's 10 megameters deep. I'm a little bit confused about what you mean by that statement. I'm assuming that in your view of how this works, the flux that is stored 10 megameters deep that's forming the sunspots is still being supplied from deeper in the convection zone or tachocline. Is that true?
Well, it's supplied from deeper layers. We don't know how deep, and this originate, particularly in the model that I showed. It's about probably in megameters, maybe like 70, 50 megameters. That's what emergence. But emergence was not in the form of flux tubes. It's actually that the structure, active region structure, is formed in the near surface layer.
So are you saying that the flux tubes are forming in that 10 megameter layer?
Right, yeah, exactly, yeah.
Okay, so it's not that the flux is being magnified there, amplified there.
No, it's not. No, it's just, it's accumulated there, it emerges. We can see accumulations there, and then it kind of gets organized in sunspots.
Okay, so it's like it's emerging faster in the deeper layers, and then it builds up as it has to slow down as it comes towards the surface.
Yeah, that's current interpretation, yeah.
Okay, all right. What other questions do we have? Do we have some hands raised, please? Irina.
Okay, I hope you can hear me now. So,
Yeah,
Yes,
we
I
can,
can
we
hear
can
you.
hear you now.
So my question is about your work in observations of helicity below solar surface. And my question is, can you discuss about evolution of helicity? Do you see formation of like a vortex like structure before a formation of active region, something like this?
I mean, in observations,
Yes, in observations.
Kinetic helicity. It's we see something, but we have not done systematic studies of this. So I don't have statistics, and I didn't prepare for this presentation. What I was mostly talking about, since we discussed coupling the surface, it's that the surface, what we see on the surface in terms of magnetic helicity. I didn't prepare a plot, but we do see some kind of, I don't know how systematic they are, but, we do see vortex flows. It just at the beginning of the emergence from emergence.
What do you think kinetic helicity can make can affect on lifetime of active regions? What is your
Yeah,
opinion?
probably does. Yeah, it probably does. Yeah, unfortunately, we don't have a fully consistent model there because it's a model that what I showed, dynamo model. It shows bipolar magnetic regions, but it doesn't form sunspots. So this part is missing. So we don't form sunspots, and probably sunspot convergent flows that we see around sunspots that maintain actually sunspots, like Elson Parker's model, and also what your simulation showed. That stability of sunspots, it's convergent flows. We don't have them in dynamo model. It's something that is it's not missing yet. So what it's but obviously I think that its effects and stability of active regions also may contribute to them, also to the whole dynamo model that currently we're just trying to find first link between active regions and dynamo. That
Okay, thank you. That's a good question. And it addresses a lot of Helicity content that we've discussed today. So let's thank all the speakers. I think we're heading into a discussion right now that's starting at 1:40. I don't know who's moderating this, maybe all of us.
Yeah, I think we were thinking of it just kind of as I like to call it, a freeform jazz odyssey.
Okay.
So I guess I would say that a really good way to frame the discussion is basically Nick Brummel's talk. I mean, he had all these nice slides where there were green check marks by things we think we know, and then red X's by a lot of fundamental things that we don't know and are still learning about. And I think the connections, what the purpose of this workshop, at least in my view, is to try to get us thinking about addressing some of these huge challenges of the disparity between spatial scales and time scales and the different physical regions. I mean, it's something that we've been thinking about a lot in COFFIES, and I think the community has been thinking about for a very, very long time. So, I mean, clearly, in order to make significant progress, this workshop would have had to been, or well, I mean, it would have to be months long, really to get into the details. But I mean, today, what we're hoping is essentially that we can at least get some conversations going, and get people thinking about some of these really tough topics. I mean, we've got a lot of really talented people in the Zoom room here today, so it would be just great if we could, kind of have a free-form discussion about where do we go from here? Is there some way we can really make progress to trying to connect all of these issues that we're really trying to get our heads around? I mean, I think of it, of course, in terms of a theory and modeling perspective. So I'm always going to be kind of biased in that way. But as I was listening to the talks today, there were, like, from a modeling point of view, there were 4 words that kind of were either said over and over again or kind of jumped out at me. And well, here are the words. I wrote them down. I scribbled them down as people were talking. Global, local, couple, and inform. So from a modeling point of view, you know, why those kind of jumped out at me is that we've got a lot of, you know, models that are designed to you know, describe particular physical areas of the sun, whether it's way down deep or at the tachophyte or in the surface layers or in the atmosphere. And there are models that are trying to combine certain aspects of subdomains of these different problems. And there are models, as we learned this morning, that are trying to do things globally and do them within one code. So the question is there what is a useful way to go forward? I mean, we should be doing all of these things, I'm sure, but there are existing models that one could inform another without actually being coupled. And there are models that are actually coupled but haven't been used to inform. So anyway, I mean, these are just random thoughts coming off the top of my head here, but maybe it would be a good way to kick off a discussion is just to think about these global issues, you know, relating global dynamics and the dynamo to some of these small scale issues like flux emergence at the surface and so forth, and then couple them to observational studies. And that's where I'm less well versed. I mean, I'm not even sure I'm well versed in the theory modeling part of it, but you know, the observations is other folks' expertise. So anyway, I don't know, maybe that's a place to start off. And also, if people had questions that they didn't get to for some of the speakers, now's the time, feel free. So I'm going to just open it up to everybody and let's go from there. Sasha.
Oh, thank Bill. You made a great introduction. I think it's exactly the main point that what we need to address. And I'd like to particularly how to link what global simulations to these turbulence models that we use. And I have a question to Andreas. And what is have you looked at say turbulence spectra in your model, how they change in depth, and also do you see what you see in terms of differential rotation in your model? Because I think, you know, the key is to everything is a differential rotation. That's what drives everything, and dynamo and the flux emergence and active regions and what.
Yes and no. So we haven't looked in detail in some into some things, but I am starting to analyze some of the simulations, and also some simulations do require more relaxation. And I kind of feel like the more I run these simulations, the more important the surface seems to become. And I keep just, okay, maybe I should put additional 1.5 megameters, and it actually does give some difference. And yeah, so but we are now analyzing some things, and there are some interesting things. I will probably not gonna say much about that yet, but there might be some really interesting results coming soon.
Okay, thank you. It would be great if you, particularly that we're interested, say, anisotropy in turbulence, you know, let's say what spectra, if you look radial and horizontal turbulence spectra,
Yes.
that was one of the key in dynamo theory.
The power spectrum and everything.
Of differential rotation, yeah, that would be great, yeah. Thank you.
You're muted, Bill.
Yeah, I'd call myself, but that would be awkward. I just wanted to make sure I was in line. A quick question, Andreas. Where is your surface? Is it in the low atmosphere, or is it like tau equals 1 or whatever?
So the simulation setup is kind of fixed to megameters. So I do see in that R equals 1 simulation that the surface kind of, at least in that demo trial run, since it's not fully relaxed, convection is not fully established, kind of raised by a little bit, but we still cover fully the photosphere. Well, I mean, we penetrate into photosphere because we have the full the dip of entropy as a surface. In other simulations, it kind of is around the same location where kind of it is initialized. So basically, we fix the mesh to geometrical locations, and then the surface could be plus minus, I don't know, a few hundred kilometers, give or take. So it's with optical surface, it's a bit more tricky because we currently don't do synthesis, but that's also in the making.
Okay, Bishek?
Yeah, thanks. I had a question to Nick Brummel about one of the things which he said we haven't done. It was regarding where do sunspots in active regions generate from, whether it's tachoclines, near surface, or the convection zone. And what I'm wondering is, what do you think, Nick? Do you think there's a way to address this question at this moment, given like the simulations of, especially Shin, the R2D2 simulations, they have been able to reproduce flux emergence from near surface, from even deeper down, varying the twist. So like my question is, do we have a way forward in terms of either solving this particular question or even making some progress, or we are basically tied to the curse of simulations and the modeling parameters where everything seems to rise depending on what parameters you're operating at?
Well, you kind of read my mind, Bishak, because I raised my hand to sort of exactly state this as what I think of is the possibly first order thing or most important thing that we need to do. And that is, you know, try and understand if realistically generated structures can survive transit upwards in the convection zone from deep down. Because we know from lots of these simulations now, if we have structures higher up, then you can reproduce things which seem to be, you know, very realistic in lots of sense. But they insert some idealized, pre-organized magnetic flux tube in there. I mean, in Toriumi-san's beautiful simulations, but it's a nice horizontal tube just inserted in there where it's convenient, right? Could it even get there? I think that is the biggest question. So, and the thing, you know, we've put, you know, lots of preconceived idealized tubes in convection and let them go, but not realistically generated structures which don't look like, you know, nice perfect flux tubes. They're still a connected non-isolated field. They're still a, you know, volume filling field. They have, you know, trailing bits, you know, overlying large scale field, et cetera, attached to them. So I think the most, I mean, it's going to say lowest hanging, that makes it sound easy, but it's because it's not easy, is to connect origination of instabilities. So, I mean, Peter Gilman and Mausumi have a whole zoo of instabilities, and we have magnetic buoyancy instabilities. We want to have an origination process for these, you know, have it with shear and everything like that, where you think this instability comes from, and then see if the structures, the realistic structures that can make, can survive convection. So you have to combine the instability calculations that we've done before with these preconceived flux tube rising things. Now, it sounds simple, like you're just adding two things together, but that's a very complicated thing. And the thing that worries me is that it's hard to imagine how you can produce magnetic field structures in these cases that are strong enough to survive the convection. So I think that's the question we have to answer first. Is it possible? Do instabilities do this naturally? They just happen to produce something which is strong enough if the shear is correct, etc., or what? I don't know. I mean, the problem is again that we can't do realistic convection even because we can't do the Reynolds numbers that we're supposed to. So we may not even get the right answer even if we try and do this. But I think that's where we have to start. Now you could do this as local models, or you could try and do this as global models. We have global models that have tachoclines. I don't think those tachoclines, fun and interesting though they are going to be realistic enough to be able to have fully self-consistent models that way. So maybe you have to force tachoclines both in local models, or if you want to try and do it in global models. And my guess is global models are easy to do first, and sorry, local models are easy to do first, and then you could maybe move to forced tachyc lines in global models and see what happens, but it's all difficult stuff. Sorry, time for somebody else to talk.
Yeah,
Gustavo?
if you can just say something on what you mentioned. So I think even before we go into clubbing up the origination of this flux tube with its rise, what I was wondering was whether, given the suite of simulations that we have seen today, you can have a pre-imposed flux tube at different depths and come up with some diagnostic to understand whether the flux tubes are getting formed very deep down or in the convection zone. Let's say like helicity measurements. Is there a modeling way to say that what we see emerging at the surface in terms of helicity, can that be tied down to where your flux tubes are possibly emerging from? Because as you said, combining these two questions, formation of flux tube by instabilities and the rise, maybe seems not so low-hanging fruit at this moment.
Yeah, I mean, I think the trouble is you can't pin surface observations to a depth unless you know under what circumstances something survives. And, you know, we've done a whole bunch of, you know, fake things traveling through convection. And then it's, you know, whether it's near the surface or near the bottom is just a matter of stratification and how strong you want to force your convection and at what relative scales they are compared to the size of your tube. So you can play those games, but until they're realistic structures, in some sense, realistic, then I don't think you can pin observations at the surface to anything because you have no, I mean, you're doing an inverse problem on where you don't understand the forward problem, right?
Yeah, thanks.
Gustavo, you had your hand up for a bit.
Yeah, hi. So I have a comment on Nick's comment, and followed by a question related to Andrew's. So Nick, if it is true that the convection zone is not really convective, or at least not the full extent of the convection zone is convective, so it will be easy for magnetic buoyancy to happen, right? And then this will make the buoyancy of structures, not flux tubes or something like this, easier to cross the convection zone. They will become very fat and big when they get to the surface, but they can emerge easily. And then I link this to a question to Andrews, because I want to know if you already mentioned that some of your simulations are not fully relaxed, but I would like to know if you see something like this Didorf zones in your convection zone, whether your convection zone becomes convectively stable or it's locally stable everywhere, locally unstable everywhere.
That's a good question. I also am very curious about that. I haven't checked explicitly, but it looks like when I look, for example, at entropy profiles, that the entropy, well, it's nearly zero, but very small. That small gradient becomes even smaller in some areas. So basically, the low entropy kind of makes deeper layers more stable. But I can't really say for certain. I need to investigate that, and that's one of the things I really want to look at.
Can I jump back in and into the things that you said, Gustavo? I mean, the whole purpose of convection is to make everything neutrally stable, right? I mean, where it's not neutrally stable is the boundary layer. Once convection is set up, you know, it mixes to neutral stability, to an adiabatic internal gradient, right? And you'll have superadiabatic, subadiabatic layers at the boundaries, depending on what you do at the boundaries. So that is always the case with convection. And so yes, any magnetic gradient is then, you know, universally unstable in the magnetic buoyancy sense. In that background stratification, in adiabatic stratification, every magnetic gradient is unstable. So yeah, you're right. There is a buoyancy force there, but that's always the case, and we've been doing that for ages. And then it's just, like I said, it's a big matter of like how strong is that buoyancy force compared to the advective effects that you get from the convection, because even though it's a adiabatic gradient, the convection is still happening, keeping it as an adiabatic gradient, right? So then it's a matter of convection versus buoyancy, and that's exactly what Bill and myself found in 2000 and whatever earlier on, is that you still have to have a very strong magnetic perturbation to make it through that adiabatic convection zone.
But they should be subadiabatic, not marginally stable, but subadiabatic. That's the Diodorf zone. So, and
well, that's only that's only at the very bottom of the convection zone, and that's due to the fact that you're overshooting.
Not necessarily. According to Petri's talk, if you have more of these random patches of cool downflows, the bigger the Diodorf zone that you get. And that's exactly the point of the paper of Henke Spruit, that when you raise the Rayleigh number to very, very high values, as there are experiments in laboratory, then you only see the downflows, and you don't see a gradient of temperature all along the convection zone. You only see downflows. So it's a completely different convection, not really local, not really happening everywhere. That's what I mean with my point, that it will be a little bit easy for flux tubes to go up in these layers.
Oh, but I mean, Petri's, I don't know if he's here to defend himself, but I mean, as Nick said, doesn't it mix everywhere? So even if it's if it's a little subadiabatic, I mean, it's going to be close to marginally stable. And so the strong downflows are still going to just coast on through the Dierdorf layer. Or maybe I'm misunderstanding, is the convection actually damped? Because I was imagining that this is sort of, the point is the convection isn't local, that it's still convecting vigorously in the region of subadiabatic. I don't know. Maybe I'm misunderstanding. And again, Petri's not here to defend himself.
It has the downflows, but it's not vigorous convection. And you can see also this in observations, right? Even 0.98 or 97 of the convection zone, you have very low power in convection.
Yeah, but we need to also remember that convection provides energy transport. So how to transport energy in downflows, because that's a Mixonal theory, the whole stellar evolution theory. That confirms by many observations of other stars. Must be careful with this. But I think Petri not online now. But I post in chat. It's very interesting that it was long old result. I didn't repeat this after this. It was from MDI data many years ago. That what we did inversions for parameter of convective stability. It was actually positive. At the time we decided that maybe that inversion is not accurate enough. So I think posted online this link to one of the papers, and we need to repeat this more carefully in helioseismology. So helioseismology provides a great test for many models, and in general, that if somebody develops emerging flux model, we'll be happy to take this data and test by helioseismology whatever we can. So that it's forward modeling is much easier than inversions testing models. So
that's regarding the transport of energy. That's the nice thing about these Diodorf zones, that even if that in the Diodorf zone you also get upward transport of enthalpy. The enthalpy transport is always from bottom to top, so there is no problem in this context on the release of the solar luminosity from the surface.
Yeah, it will be good to calculate this. What I wanted to ask Petri, but he left. We'll talk to him later.
Yeah, but I mean, Gustavo, I think all convection simulations that don't have a completely solid lower boundary show this at high enough Rayleigh number or Reynolds number at least. And I think the point is you're talking about the end state of a well-mixed calculation, right? It's still convecting. I mean, you can't just have low entropy rain and not convection. You can't have it on its own. Low entropy rain everything else adjusted as in a global scale to what low entropy rain is doing. And so that's what you see. I mean, you get a Deardorff layer out of that, but then the enthalpy flux is still up. I mean, that almost by definition is convection.
No, convection by definition is when it's Schwarzschild unstable.
I think convection is when the convective flux transport is the thing that's doing the heat transport.
Well, so in mixing length theory is not.
Well, mixing length theory isn't convection.
Yeah, but that's
a horrendous approximation to convection.
That's where everything takes the flux of the enthalpy, right? So whenever you have a Schwarzschild unstable layer, then in every local point is unstable to convection. And then you transfer energy. But this is non-local transfer of energy. This is non-local convection. And still the transfer of energy is upwards.
Yeah, absolutely. I agree with that. But I mean, you talk about Schwarzschild and unstable, but when you impose your low entropy rain, I mean, you're imposing a difference between the top and the bottom. There's a global difference in this thing, which is the thing that drives global modes. And you see local elements of it and you see global aspects of it. And like you said, the transport becomes non-local because of big downflows and stuff like that. So yeah, I mean, that is still convection though.
Lauren?
Yeah, I mean, I guess this whole discussion, like Deardorff layers aside, I mean, I think the question is, could the convection be weaker than we think and therefore allow for super equipartition magnetic fields? And I think the problem with that is the convection is what's producing the magnetic field. And so, I don't know, super equipartition dynamos are difficult, right? Because somehow the magnetic energy source has to be, the source of the magnetic energy has to be smaller than the magnetic energy itself. And I'm not sure exactly how to achieve that.
Yeah, and that's why I say you need to talk about the origination process, because maybe you need some sort of confining mechanism or strengthening mechanism, or we know the stretching and stuff like that, but maybe the instability has to create patches which are super equipartition. Now the whole thing probably can't be super equipartition, but if it creates patches of stuff which is, then maybe those are the bits that we're seeing.
So I wanted to make sure we're also having bits of our discussion focused on the observational aspects of all this. Amy, did you have any thing you wanted to bring up, or any discussion area we wanted to address on that end?
Yeah, Amy, you're muted.
I'm currently obsessed with activity nests and active longitudes, and I think that there's some interesting momentum in this group right now about that. But I still, it's not clear to me, even if we identify, let's say we fantastically identify like two, active longitude modes that persist for the entire solar cycle. I mean, our interpretation of them would still be, it still feels like our interpretation of them, we don't have a good handle on how to interpret them. So I don't know. I mean, I guess my questions would be, for the modelers, I know that both Nick Featherstone and Lauren Matilsky have had some results in modeling that show something that looks like persistent flux emergence. I think in Lauren's case, it's two hemispheres. It's the two different hemispheres showing opposite sides, right, of flux emergence. And they actually have some strange polarity phenomena with them, like they look anti-Hale. One of them does, I believe, Lauren.
Yeah, I think that's right. Well, we don't have flux emergence. Well, I don't have flux emergence. I just wanted to clarify that.
I understand. It's indicative of what might become an active activity nest or active longitude. And then in the case of Nick Featherstone's modeling, which I believe Kinfei is also part of, maybe some other people in this group. It appears to be an interaction between the convection modes and the magnetic modes, which I don't really understand where those magnetic modes are arising from. You said that the magnetic modes were being formed by higher order convection modes, I think is what you said. Is that true?
Yeah, I think the way to think about it is there's a range of these modes. It's not in our models, it's not a huge range in M, for instance. And if you thread those kind of columnar things with a magnetic field and let downflows take part, you'll naturally form power on those same scales. And so what you're seeing is kind of power on one magnetic scale that's formed interacting with convective power on another scale to form an EMF, which then gives you magnetic power on a low frequency, low M scale.
Okay, so let's say Junwei's results with Reju become much more statistic, or he convinces himself that the research is statistically significant, that the M=4 mode that he sees is, I believe it was prograde. Can tell me if I'm wrong. But let's say he sees a strong M=4 mode that's slightly prograde. Would you be able to interpret that in your model in any way?
Yeah, well, I think the real question would be, what is the frequency of that mode with respect to the rotation period? And then you've got spatial wave number and temporal frequency, and you can start to kind of compare those to models. Not just mine, you could compare them to others as well.
And so that would give us some information about the convective spectrum or something, or
Yeah, I think that's a good point. I think if we were, like you said, if Junwei's work progresses and he says, okay, here are the statistically significant magnetic features that we see, and they're at certain M and certain omega values. And then if you have a nonlinear model that is naturally reproducing those, it's very suggestive, right? I mean, then what you would want to do is understand, like the models that I showed are very laminar. You would want to understand, can you also see signatures of this and things that are not so laminar? But yeah, I think to me, that was kind of the really interesting bit of what Junwei presented, was that it's telling you something else about the system. We have really strong observational constraints from the differential rotation, say, or the surface meridional flow, the butterfly diagram. But here's something that's kind of different, right? And that's interesting.
Well, something that I haven't presented here, but I've talked about a little bit in our group meetings, is that I'm finding really strong asymmetry across the equator for the activity nests. And I'm working on showing its statistical significance. I do think that it is statistically significant, which, if that's true, and it would, to me, it would indicate that this is not large scale this is not the large scale convection that crosses the equator, so that it would be symmetric across the equator. So like I said, I'm still working on showing the statistical significance of this, but I do believe right now, my leaning is that this is true, that the different nests that we're finding are not symmetric across the equator. And the longitudinal distribution of active regions is not symmetric across the equator. And it could be that it's anti-symmetric, but I'm not searching for that right now. That would include another way of looking at the parameter space. I'm only finding that it's asymmetric right now. But like I said, it's preliminary results, so need to figure that out. But your modeling would show symmetry across the equator right now.
Yeah, it depends which field component you look in, but yeah, it's either symmetric or anti-symmetric. It's not, for the most part, it's not asymmetric. That's correct.
What would be anti-symmetric about it? The flows?
No, well, the flows are, yeah. So the latitudinal flows are always pretty much anti-symmetric when you've got thermal Rossby waves.
But what would be anti-symmetric then?
Well, so if you've got flow moving away from the equator, right? So toward the North Pole or toward the South Pole, you see that. And then I'm trying to remember, one of the components of the magnetic field is also anti-symmetric. So you have positive polarity in the north and negative polarity in the south.
But not, say, a prograde magnetic bundle in the north and a retrograde in the south.
No, I mean there are some dynamo models that have hemispheric asymmetries that people have published.
But there's a lot of inertial modes that are anti-symmetric across the equator.
Anti-symmetric, yes. I don't know so much about asymmetric.
Yeah. Well, it's just the way I'm searching right now is this unable to determine anti. It's only able to determine asymmetry. But anyway, that's a very specific point. So I think that there is some momentum around the active longitudes or activity nests, whatever you want to call it. I think COFFIES, the group here, could make some headway on that, and that we should stick to that. In terms of other observational aspects of today's work, you know, I find the observations about the near surface shear layer or the leptocline really fascinating. And I think I don't fully understand the implications of what was presented today. I don't know if anybody else has some comments about the near surface shear layer. I don't know if Christina's still here, but she was showing solar cycle dependency, right?
Yeah, I'm here, but I don't know the implications of my findings. So yeah, I found it interesting because it is such a sound speed variation. I mean, there is a change exactly where the shear are, like 2.5 megameters, but yeah, a variation of I don't know, Amy.
I mean, could it be that just there's buildup of flux that is changing the, you know, the conditions at that layer? I mean, just simplistically, that's what I would imagine.
Yeah, I don't know. I'm not going to speculate on that.
No, I think what I don't know, Irina is online or not, but in Irina simulation, it's actually that was the boundary what these ionization zones, and that was
What?
zones of ionization of hydrogen and helium that at these depths, and that what changes properties of convection, and that what I think that what.
So it's not actually an influence of flux in any way. It's
no, it influence Reynolds stresses because it's properties of convection change across this layer.
Right, but that wouldn't change with the solar cycle, right?
The solar cycle, yeah, solar cycle. I don't know why that what we see is this accumulation of magnetic flux in surface layers, but I have no idea. We don't have model for this. Actually, we do have model, but again, that what altered in the simulation when this model in a pore, because it's conversion flows, you know, it's similar to Parker's model of sunspot. Conversion flows form and maintain compact structures like sunspots. And that's probably that what as deep as they go, these conversion flows. And but I'd like to point out that another proposition problem that is that magnetic helicity, that what we found that there's now a strong link between, because in magnetic helicity balance is one of the key in dynamo models. And that probably what affects strength of solar cycles. We still don't know why solar cycles are different. But it's possible that magnetic helicity plays significant role, and that fluxes of magnetic helicity through the surface may play important role. And we have some predictions that actually testable on observations of how the fluxes are distributed during solar cycle. I think that what and also fluxes in emerging active regions. Now we it also it affects, you know, what I showed this modeling of twist and tilt of active regions that would house helicity, that relates to magnetic helicity. So what in Dynamo team we are planning to, I'm planning to organize a series of discussions on this topic in both models and observations, and about that what role of magnetic helicity in and loss on the surface.
Yeah, I definitely agree that helicity is a crucial observational constraint and something that can influence solar cycles and the.
Yeah, there's many people, hundreds of papers, you know, people studied, but they did this how it's called local correlation tracking, measuring of velocity and then calculating helicity. But probably that what we think that a lot of magnetic helicity is unresolved, actually in turbulence. It's not resolved in observations that are generally a low resolution, like HMI.
Yeah.
I think I interrupted. Irina wanted to say something. That was.
No, it's okay. Just you actually give me time to think a little bit about leptocline. So it's hard to say impact of leptocline on time scale of solar cycle. But what it definitely does, it affect on turbulent properties of convection and also diffusivity, and it may change. It actually may explain why active regions or or flows start suddenly change properties closer to photosphere.
Wait, when
Basically,
you say it may explain, what do you mean by it? Do you mean that?
Okay, so what usually when we discuss about say emergence of magnetic flux, we consider conditions, background conditions, which vary kind of slowly as we approaching closer to surface. I mean, changes in density, temperature, like, I mean, thermodynamic properties.
Mm-hmm.
And but our simulation results actually show, if you consider variations of density or temperature, we see actually change in variations in this layer. It is first thing. And second, what Sasha already mentioned, because we have rotation and such a change in thermodynamic properties may affect on distribution of Rayleigh stresses. And in my vision, it potentially can be layer where magnetic energy may accumulate. You see?
Mm-hmm.
It's kind of like something similar to subsurface shell layer, but on a smaller scale.
Yeah. Okay.
Well, is that consistent with what Christina showed about the magnetic activity index in the northern and the southern hemispheres being related to the variations in the gradients at the upper levels? If I was interpreting correctly what Christina was showing.
The change of the shear with MAI is stronger in the northern hemisphere than in the south.
But that's consistent then with the magnetic field having an influence on what that gradient is, right?
Yeah. Yes. Yeah. Good.
Which I think was related to what Irina was just saying.
Okay.
Does anything new come out of today's discussion in terms of projects that we want to work on? I mean, we talked a bit about, well, global and local and connecting and informing, or coupling and informing were all sort of words that, Bill sort of keyed in on. And I'm just wondering if anything practical comes out of today. Is there a project or something that COFFIES could help with that would be related to any of those, in terms of, setting ourselves a little goal, or recognizing that there's something that we could make some real progress on that would be helpful. A lot of the talks I heard today were, one group reporting its own thing, and there were some, but not a lot of people working together on things from between different approaches, maybe. And so I'm just looking for things where we can make those connections.
Oh, I would also add too, Todd, that it can be collaborations outside of COFFIES too. So.
Oh yeah, sure. We'll take credit and give blame anything that anybody wants to do. I mean, the real point here is we want to make progress on the science, right? And that's why, if there's something we can do in COFFIES to facilitate that, whether we're paying you or not, that's great.
Yeah, I think Amy just also already mentioned this. Today I showed some preliminary analysis showing that the intersection of retrograde and prograde modes or wave patterns are the locations of the super active activity nests. So I think this, since these are the preliminary results, we're not sure if this persists throughout different cycles. But if this persists, I think this is a very good topic for theories and modelers to work on. Previously, there were a lot of discussions about magneto-Rossby waves, the connections with active regions and the magneto-Rossby waves. But here, this is a slightly different idea. Maybe the super active areas are intersections of different field modes, prograde and retrograde modes. Maybe this is some new ideas worth exploring in the future.
Well,
I agree.
I agree. I certainly think it's interesting. And like I said, I think it provides an interesting potential observational constraint on models, right?
Right.
Getting close to the end time here. Just a couple of programmatic things before we go. Let's keep the discussions open, and to Todd's point, let's take some of the momentum here and try to translate it forward. A quick question to those who set up the Slack: will the Slack be active going forward? And also, I wanted to ask, will the Zoom chat be saved along with the Zoom session?
So I've saved the Zoom chat.
Okay.
So it's saved locally for me. The Slack channel really doesn't have any scientific content. So maybe I will just disband it after this meeting is over because we already have enough Slack channels. So.
Well, I also, on the other side, if people wanted to continue the conversation, especially people who don't have access to the COFFIES Slack, it might be worth keeping it open so that conversations can continue. But I'll let the organizers decide that.
Okay. And the workshop itself will be posted on the COFFIES site. Is that correct? The Zoom, I mean.
Yeah, I think the recording, and if anybody, I believe Raju will reach out, but if anybody does not want what they presented, the recording of it shared, then we can edit things out. But otherwise, the plan is to post it on Zoom.
Okay, Sounds great. On behalf of the organizers and COFFIES, I'd like to thank everyone from all the totally different time zones, from making a full day of it here. Thank you to all the speakers. I know how hard, it's an impossible task, you know, to fit so much complicated stuff into 10 minutes. But you guys did great, and we really appreciate it. And I hope everyone found it a useful way to spend Friday. And with that, unless there's any other comments or questions, I think we can bring the meeting to a close. All good?
Great
Okay,
stuff.
thank you so much.
Thank you
Okay, see
very
you guys.
much.
Thank you.
It was great. Thank you.
Bye-bye.